We are recording now. Yeah, we'll still give it a couple minutes for people to sign in, so we'll wait for like maybe 3 to 5 minutes before we actually start the talk. You guys can just keep chatting if you like.
Now you have to call CQDX and we'll be listening. And if you have anybody interested in coming back, then we'll join, right?
That's right, exactly. We've got Chris Deacon on as well.
Oh, great. Hi, Chris.
Where is he?
I can work out how to unmute. Hi, Ben.
Hi, Chris. Well, it's better if you don't have a transmitter than if you don't have a receiver, right?
Absolutely.
Hey Ben, did you ever get in touch with Ned or Ed Hare? Did they answer you back?
No, I have to remember. I got a mail that he hadn't had no time and would come back later. I think but I don't remember which one.
Okay, that was probably Ed.
Okay.
Because I saw the introduction email go by, but I didn't see anything after that. So I was hoping they wrote back to you.
Yeah. It would have been great if they were here right now, but I don't know if they are. I even
so Ben, I'm working with Juha Virinen. I'm trying to get a passive ionoson receiver set up at my house now. And Dev has been trying to get one running down at the university as well. So I just got the hardware set up at my house 2 days ago, and I'm testing some stuff. So I've got a USRP, and I'm using Juha's GNU chirp sounder code. So see if I can get anything out of it.
What do you have that running on, Nathaniel?
I have an Edis USRP, and I have a Dell Core i7, 4-core, 8-thread machine with 64 gigs of RAM.
Okay, I was just wondering if it was a PC or a Raspberry Pi.
I've got a real.
But you're using the DX engineering loop, Nathaniel?
For this down at the university we are. For this one, I have it plugged into my ZS6 BKW. Which is up about 30 feet in my trees.
Yeah, that's good.
Yeah.
And I think most signals you will see at the lower frequencies anyway. So there the ZS6 BKW will do fine, I guess.
Yeah. Yeah, we'll see. I haven't seen any useful ionograms come out of this yet, but as I said, I actually just got the whole thing hooked up yesterday, and I still don't fully understand all of the controls and scripts. So I don't think I have all the settings correct yet. So I think with a little bit more
I'm very interested. Yes.
I have my system is processing things as we speak, and I keep watching it. I'm very hopeful that at some point it will say that there are PNGs that appear here. But I think I recorded about 3 hours of data this morning, which comes out to be about 1 terabyte, and so it's doing post processing on that right now. So yeah.
What sounders are you expecting to be able to pick up?
Definitely the one in Virginia, I think. Maybe the one in Puerto Rico. There's one in Texas I know about.
Is there one at Haystack?
I think there is, but this code only works with chirp sounders. So
right, that one's a regular
a
Lowell Digison.
Yeah, so I don't think those are more complicated to decode, but I'd be very interested in learning how to decode those as well. But yeah. Anyway, I think it's now 3:05. So I think we should get started. So once again, I would like to welcome back to the HamSCI Telecon Ben Witvliet. And so Ben is going to talk to us today about radio noise propagation and measurement. And so He is going to say, especially below 20 megahertz, the ambient electromagnetic noise or radio noise limits the reception rather than the internal noise of the receiver. And so Ben's going to talk about propagation from the noise source to the receiver, elevation, angle, and polarization. And he's going to present HF radio noise measurements in quiet rural environments in which different noise sources can be distinguished. And he'll also demonstrate by measurement that in a quiet rural area, most of the radio noise arrives via skywave. So furthermore, he's going to talk about the radio noise measurement methods. True radio noise measurements are challenging, especially when in quiet environments. Sensitivity and linearity and engineering skills are all needed to design the setup and interpret the results. Also, the presence of weak and variable legitimate radio signals in the spectrum pose a challenge which adaptive filtering may help. So he will also talk briefly about the activities in the ITU Study Group 3, which he is a member of, and the need for more measurements outside of Europe. And then there will be questions and answers at the end. So Ben is Papa Echo 5 Bravo, and he is a doctor of engineering and has been a ham radio operator since the age of 13. So I think with that introduction, you can take it away, Ben.
All right. Can you see my screen?
Yes.
Yes.
Good, good, good. Oh, this is going very fast. Okay, I hope you didn't watch because then you've seen the whole presentation already. Good. But let's start at the beginning. So good evening from this end. Good morning to Brazil. I didn't look through all the people, so I may have missed some DX. My name is Ben Witvliet, and you pronounce that Witvliet. And of course, you write it completely differently, but that's because Dutch people are crazy. I've been a radio amateur since 1974. I started as a shortwave listener, and I heard 300 countries on this old vacuum tube receiver. I didn't want to become a radio amateur. Listening was just fine until I went to Monaco for work. And then I really wanted to have that call sign to talk to my dad, who is also a radio amateur. My current call sign is Papa Echo 5 Bravo, which is nice and short in CW. As I just said, I lived abroad quite a bit in different countries, so I have a couple of exotic call signs as well. And I made a career from my hobby. I worked in industry, mainly in broadcasting, in government, and in academia. This was one of my first jobs. I was an apprentice at Transworld Radio in Monte Carlo, doing a lot of studio work, but also assisted with antenna measurements on the medium wave transmitter. They had 1.2 megawatt with two elements array beaming north. And they also had quite large setup for shortwave. I had my own radio station with me in Monte Carlo Harbor, but with considerably lower power, of course. This is a more serious job, my dream job, really. I worked as a chief engineer at Radio Netherlands in Madagascar with all Malagasy staff, a total of 50 persons. And we operated two 300 kilowatt AM transmitters around the clock, shifting frequencies from hour to hour. And we had 13 high gain slewable curtain reflector antennas. And at this location, I also had my dream call sign, 5 Radio 8 Delta Sierra. I would come home at 4:30 in the afternoon and would switch on the radio on 40 meters and would have corridor hop to California and people shouting already before I even mentioned the call sign. Back in the Netherlands and still getting better from the 5 Radio 8 that I lost because I now had a normal call sign again. I worked for the Netherlands Broadcast Transmitter Company. And this is one of their masts. They had 6 of these masts higher than the Eiffel Tower with a lot of transmitter power on them. And at December, they will string lights in the guy wires so that it becomes a Christmas tree. Since quite some time, I'm now work for the Radio Communications Agency of the Netherlands, doing all kind of applied research and international standardization. This is a measurement system that I created together with a colleague of mine. We designed it and realized it. It's to fly around FM broadcast towers, measure the antenna diagram really accurately, and also the effective radiated power. Still, regardless of all that nice work, I got bored in 2011, so I started doing my PhD research in spare time, in part-time, sorry, a lot in spare time as well, on near vertical incident skywave propagation and antennas, and I promoted in 2015. Today I'll be talking about ambient electromagnetic noise, or radio noise, and the category of that which is important for us radio amateurs, which is man-made noise, the propagation of radio noise, the influence and the role of the International Telecommunication Union with respect to radio noise, and the impact of one of their recommendations, which is called P372, Propagation 372, on spectrum management and thereby also on you. And of course, as I promised, I'll tell you how I try to measure radio noise and what's important to know if you want to measure radio noise. Questions preferably at the end, that's more efficient. If you look at the lower right corner of the sheet, you see a number. So please mark it down with your question so that we can quickly skip back to the right sheet. Let's start with what radio noise is. Well, it is everything that's present when the frequency is not in use and you're still listening to it. So if you are in a very good location, it will only be natural noise. So comparable with audio noise, it would be the wind in the grass or birds singing far away. And in radio, in electromagnetics, that noise is generated by quite exotic sources. So atmospheric is caused by lightnings, can be an individual storm or something very far away, like in Africa. Noise from the Milky Way, still further away, emissions from the sun, radio emissions from Jupiter, pulsars and whistlers. And all those phenomena have been intriguing since the beginning of radio. People in the 1930s connecting their receiver to an antenna heard all kinds of crackling noises and they had no idea where they came from. So people like Potter studied them extensively. Also another famous person, Mr. Jansky from Bell Labs, did research on radio noise and tried to find out whether it had a distinct source in some direction. So he created a 20 megahertz very directional antenna on a merry-go-round. He let it rotate on, and then at the same time registered the output from the receiver. By doing so, he discovered very unexpectedly that the Milky Way was also a big radio noise source. And that started radio astronomy. Then there's another phenomenon in the very low frequencies, also a radio phenomenon that's very interesting, which is whistlers. They sound very musical. I won't play them right now, but please look at the link that I provided. They're very, very weird sounds that nature produces through plasma physics. On top of that natural noise, there's something that we call man-made noise. It's much louder. It's generated by man or by devices created by man. And it's comparable to the birds and the grass and the wind, to these roadworks where you cannot hear yourself breathing. Radio noise, man-made radio noise is generated as a waste product of electrical equipment and electronics, lighting, wired communication, and spurious emissions of transmitters. To be sure, it's not the intended transmissions. Those are not radio noise. It's all the byproducts of transmitters. To illustrate that, I have a real-life measurement that I made for you. This is in the 8 megahertz band over 24 hours. And the z-axis, the vertical axis, is intensity in decibels. This looks like just dirt, but if you look very carefully, you see several intended transmitters that are on a steady frequency and switch on and off. You see a thunderstorm just after noon, which is wideband because it's impulsive. And at night, when everything else is quiet, you see a switch mode power converter, which may be 2 kilometers away. This is in a very quiet area. It probably arrives via ground wave. It can be distinguished by the multiple carriers that you see that are harmonics of the original switching frequency, and also that they drift through the frequency. In the evening, you see something similar. They may all be small interference sources that combine from a lot of small houses where people arrived in the evening, maybe TVs, maybe other equipment that they are using. And then in between all those dirty emissions, all those polluting emissions, you see the background natural noise. It's lower and it's more steady. But if you watch carefully, you see that even that background noise is not just one value. It changes with the propagation. So this is 8 megahertz. The band opens on the day, so there's a lot more noise coming from a lot of directions throughout the day. And late in the evening, only the X is coming in because of the lower critical frequency, and the total amount of noise is lower. This is a graph of that noise, of the background noise, and here you see the same thing. It's very clear that propagation has something to do with the incoming radio noise. But can we prove it? Well, let's first talk about the propagation of the different sources. First of all, extraterrestrial noises can only be received when the ionosphere is transparent, so above the critical frequency. Then if you have man-made noise from big cities on the left of the figure, there are 3 different propagation paths. One is ground wave. The other one is line of sight if you're very close to the city. And the third one is sky wave via the ionosphere when you're below the critical frequency of the ionosphere. And something similar is the case for atmospheric noise. If you're close within range of the lightning thunderstorm, you will hear very loud and very wideband crackling noises, really impulsive noises. But there's also noise coming in from thousands of kilometers away from big tropical thunderstorms. And they sound more like a little bit irregular white noise. Due to the different propagation mechanisms, we can also say something about polarization. The ground wave polarization is vertical. Skywave propagation via the ionosphere consists of 2 circular polarized waves that interfere with each other, so resulting in some somewhat random changing polarization. And the extraterrestrial sources are unpolarized. Now, this is normal propagation. Can we in some way prove that noise is coming in via this propagation mechanism? Well, we can if we cleverly use the nature. This is NVIS propagation, so below the critical frequency. But what happens if X-ray flare of the sun strikes? Look at this. Then there's suddenly a very intense ionization of the D layer. And the D layer has a very high amount of neutral molecules, so the absorption will be very high at that moment, making radio signals attenuate a lot, and an HF blackout is caused. Well, let's see what happens if you are registering during an experiment and you have a solar flare. This is a couple of years back when I was still doing research for my promotion. I had a transmitter on the air in the 40-meter amateur radio band with dual circular polarization. That's a signal that you see in the middle. And it's in the amateur radio band, so you see a lot of other signals as well. Then at this moment, a solar X-ray flare struck, and I didn't know it. So I saw the signals drop by 45 dB. First thing, I got out of the car that we had the equipment in to look outside at the antenna. but the antenna was still there. Then I took apart the receiver, I checked it with a signal generator, and it was working as well. So I quickly reconnected it because of the experiment. And I didn't understand it until then I looked at the NOAA site and I found that it was an X1.6 flare right at that moment. And it gives a very interesting addition to the research. You see that about half an hour, 35 minutes, there was a blackout, and then there was gradual recovery. And after 3/4 of an hour, all signals were back to normal again. Importantly, you also see that the radio noise is dropping quite a bit. Generally, if I do these experiments, I go to a quiet rural location because then I have the maximum signal to noise ratio for my experiments. And then also I make sure that my receiver is still more sensitive than the noise that I receive. So that I'm really on the edge of what is possible. In this case, the noise dropped 13 dB, close to the receiver noise, and it became dead silent. 13 dB, that's quite a bit. If you calculate what that power is, that means that 95% of the power disappeared. Only 5% was retained, which means that the background radio noise arriving on 7 megahertz on this location, a quiet rural location, constitutes 95% of all the noise that I receive. Okay, I promised to talk about the ITU as well. Well, the ITU, you first have to understand where it comes from. It's part of the United Nations, and it is been started because the need of frequency coordination between countries. The international telecommunication consists of 3 sectors. The most interesting one for us is the radio sector, and the work in the ITU is done in study groups. And one of them is the study group on radio wave propagation, which has another subgroup, which is the working party 3L, which concerns itself with ionospheric propagation and radio noise. They make models of propagation that you can use to calculate things, and also models of radio noise. And one of those models is described in recommendation P372. P for propagation and 372 is just a number. And I'm a member of study group 3. I work there from time to time because I'm part of the radio agency. So there I represent my country. Why does the ITU have a recommendation on radio noise? Well, radio noise, especially between below 20 megahertz, is very important if you design a system or if you want to study the effectiveness of a radio system. And that's because the ambient noise is so high on low frequencies. I just give you a sketch of a transmitter and a receiver over here. You see the signal from the transmitter arrive at the antenna. You see ambient noise entering the antenna. And you have the first stage of the receiver, which is generally the dominant noise source in the receiver itself. If you want to know the sensitivity of your system, you can calculate your signal to noise ratio, which is the signal power divided by the total noise power, and the total noise power is a combination of the ambient noise and the receiver noise. Now in the lower HF, where the ambient noise is much stronger than the receiver noise, your signal to noise ratio is completely defined by the ambient noise. So the ambient noise level is directly telling you what the sensitivity is of the best system you can design. In P372, you find the expected levels of natural radio noise, so curves versus of intensity versus frequency for atmospherics and galaxy noise, etc. And you can also see levels of man-made noise, and those noise levels are distinguished in city, residential area, rural area, and remote rural area. And that's because the number of devices and thereby the interference is different in those areas. How do they describe the noise? Well, they could have described the noise field strengths outside the antenna, but traditionally already since the 40s, they've done differently. They defined it as a noise figure, as a factor, a noise factor on top of the thermal noise when you look at the output of a lossless monopole antenna. So that's a theoretical antenna. Every antenna has losses. But if you would calculate a theoretical antenna, that one is used for these levels. And the noise figure in its logarithmic form is used in most tables. This is one of the tables that describes man-made noise in P372. Man-made noise is shown as straight lines. On the vertical axis, you see that ambient noise figure. On the horizontal axis, you see the frequency scale, logarithmic scale. And you see different lines for city, residential, rural, and quiet rural. And there's quite a difference between city and quiet rural. It's about 32 dB or so, so from the top of my head. These curves haven't been changed since the 60s, although there's a lot of pressure on them to update them, and I'll show you what effect that could have. First of all, it's important to know that if the radio noise levels in P372 increase, more interference will be allowed. So it's not as a lot of people think that if you prove to the ITU that the radio noise levels are increasing, there will be a strong reaction and the EMC norms will be changed so that the noise will go down. No, they just document the status quo. And that means if there's a new system, for example, a wireless power transfer that causes a lot of electromagnetic pollution, but they measure that level and compare it with what is in P372, and the levels in P372 would be extraordinarily high. They say, my system is not a problem. And there's a chance it would be acceptable in the ITU, in the World Radio Conference, or in local legislation. To explain that, if this would be your backyard, well, if so, you would have good ground conductivity. I would still move. But then if there's somebody with a truck load full of rubbish and would put it there, you would probably hardly notice. So that is if the noise levels are high and you would have a polluting system. This is a different picture. This is my favorite beach in the south of Portugal. I sometimes go there winters. It's beautiful, quiet, very clean. So if you would do the same here, it would be an outrage and people would really find you. And that's the difference between city and quiet rural. Now, some ITU members that did a lot of measurements claim that quiet rural does not exist anymore. That's a danger. So what they propose for the revision of P372 is we scrap quiet rural. Quiet rural does not exist anymore. So we only have 3 lines, and the difference between city and rural is not that big. It's about 10 dB, 12 dB. So the whole interference limit shifts upwards by 14 dB. Other ITU members, and not even small members, I won't mention them, proposed even weirder and more drastic changes. This is an example which was proposed and defended quite strongly 2 years ago until we killed it. It has no quiet rural curve in it, so that's the first crazy thing about it. Then the second one is city is apparently rural in the country that claims this. And there are no values below 5 megahertz. So what do we do below 5 megahertz? Are we extrapolating these curves? So are we coming to 110 dB at 1 megahertz? Let's hope not. I was in SG3, so I've been able to kill this one, and we're working on something better now. So what you just saw, these last 2 sheets imply that affirming and measured by measurements what the quiet rural levels are is highly critical. If other people claim they cannot find any, we have to find them. And that's much more critical than measuring city or urban levels, because that quiet rural level is the baseline of all of them. Just Curix, need some water. I would give a biased picture of the ITU if I would not also present some good measurements. This is from a party that measured in 2018 and measured from 470 kilohertz, sorry, to 50 megahertz, and has shown also that there's still clearly quite rural positions to be found, even in pretty dense populated countries. Here in their measurements, the difference between city and rural is 18 dB, and between city and quiet rural is 30 dB. And that's more like what we radio amateurs experience in daily life. Regrettably, although P372 is a norm that should give guidance to people around the world, the measurements come from only a very limited number of locations. Japan did a lot of measurements in VHF, UHF. In Europe, it's the Netherlands, Germany, and the United Kingdom that did a lot of measurements, both in HF and VHF. And then in the UK, in the USA, I only have a handful, I think 10 or 12 measurements in Boulder, Colorado. And that's everything we have. So we could use a bit more. What's the noise like in Africa? What's the noise like by you all in the United States? What's the noise in Papa Yankee 2 land? We would be very interested in that. So how can we measure noise? Well, first of all, you need a good receiver. It needs to be sensitive, otherwise you will be measuring the noise of the receiver alone. It needs to be very linear, otherwise you will measure noise created by intermodulation products created in your own receiver. And it needs to be clean or pure because you don't want to have a measurement of your own phase noise that is superimposed on and intermixed with a lot of strong carriers. So you have to be sure that what you measure is truly there. You can use an expensive Rode and Schwarz receiver for it. We did in the past, a receiver of 150,000 euros. But an HPSDR, 16-bit HPSDR is probably even better than that Rode and Schwarz receiver. And of course, we are very hopeful for the Tangerine SDR because my HPSDR costs 4,000 euros. So I won't leave it outside with me somewhere in the neighborhood. With the Tangerine, I could. Then another word of warning, you can use any receiver and put an LNA for it and then say it's sensitive. Please don't use a preamp unless you are really a receiver expert. You have to align intermodulation, noise, and signal levels from the preamplifier and the receiver. And there must be at least 50 ways to mess up your specifications. So what do we need for an antenna? Well, I always prefer a passive antenna because then you know it has no noise itself and it's linear. But then you need a passive antenna that's very efficient. At least if you want to measure quiet rural noise, you have to have noise that's strong enough coming out of your antenna to be measurable. The reference antenna of the ITU is since the 1940s, a short, lossless vertical monopole above a perfectly conducting ground plane. Well, lossless is something difficult in real life, and perfectly conducting ground plane and then infinitely of size is also not very real. It's a mathematical standard. And if we use a practical antennas, we have to relate it to this theoretical antenna. So what do I use? Well, I did a bit of measurements with quarter wave vertical because it's very effective. It has a high efficiency. You can put it on with on-ground radials. And you have to still compensate for the ground loss because the radial network is still primitive to a broadcast station, for example. So you can easily have 6 dB ground loss even with good soil below it. Then you have to check whether you have any mismatch, preferably not. Otherwise you have to account for the mismatch loss, for the cable loss, and for any ohmic losses, which in my case are very low. And this is a narrowband solution. So you have to switch the antenna for every frequency that you want to measure. or you have to make a trap vertical and make sure that also your ground system is effective on all the frequencies. You should not consider antenna gain. That's a misunderstanding that a lot of people have. Antenna gain has nothing to do with your radio noise measurements. I'll explain that to you. I put the formula on screen. Antenna gain is created by directivity of the antenna. So there's an advantage in one direction, and it takes its energy from other directions. And if there's losses, it's multiplied by the efficiency of the antenna. Now, if we do radio noise measurements, we assume that radio noise is coming from all directions. So if there's one dominant source nearby it, that will not be correct. But if you're in a location and you want to measure the general noise that comes from all directions, you must assume that it comes from all directions. In that case, if the gain is more in one direction in the other, but the noise is coming from all directions, it doesn't make a difference. You will have gain in one direction and less in the other one, and the amount of power will still be the same. So I have the same noise power coming out from an antenna that is not omnidirectional, not that well omnidirectional. Efficiency, however, is very important because those losses are directly attenuating the noise coming out from your system. Can we use other passive antennas? Yes, an inverted V antenna is just as well. Then you won't have those ground noises, ground losses so extensively as with a vertical antenna. It will be directive, but as long as your noise sources are not in one particular direction, the measurement will still be valid. And if you don't believe that, I'm generally quite critical with my own measurements. Then you put up two inverted V's and you put it to a dual channel receiver. You demodulate both signals, you measure the radio noise in both channels, and then you add up those figures. What about active antennas? A lot of people have active antennas for reception, but those are quite complicated if you want to do a calibrated measurement with it. First thing that you will have to check is, do you really hear radio noise or do you only hear the antenna noise? That's not the case for most antennas. Also, the DX Engineering RF ARAV 4.1, a vertical antenna, does hear his own noise if you put it in a quiet rural area. So you need a good measurement method to distinguish that. Not switching off the antenna doesn't work because switching off the LNA will cause it to attenuate and you will not have a good reference. So you would have to put the antenna in some anechoic chamber or shielded chamber or so, and then measure its own noise. Also, because there's an amplifier in the antenna, there's a possibility of intermodulation. And if you have intermodulation, you get the same problem again as I posed before on the LNA before a receiver. You will have to be a very good radio engineer to first measure all those products and effects in the active antenna, and then match that to the receiver values to get the optimum results. And then, of course, you have to calibrate it. You cannot simulate an active antenna. You really have to calibrate it because it's a mix, a hybrid between something passive and something active. So now we have a measurement system. What do we measure? Well, we have the wideband noise, the background noise that I've shown you, that is random in time and more or less flat in frequency. Then you have something that the ITU calls single carrier noise. That is those noise bumps that are drifting through the frequency that are above the wideband noise. And then you have impulsive noise that we all know so well. So impulsive noise is good, you can see in time. But in frequency spectrum, it's wideband. I won't explain all of them. I don't have the time for that. I'll take the wideband noise as the easiest example. This is, again, a part of a waterfall diagram of a measurement that I made. So I normally stream the data from my HPSDR2 disk, then make a FFT, a fast Fourier transform, so that I can create a waterfall spectrogram. This is in the X window of the 7 megahertz band on daytime. Still, you see a couple of signals coming in. There's the background noise below it. Of course, you can just select the frequency and take the noise from there. There's something more elegant. You can make an adaptive filter that takes out all those frequency time samples of the radio signals, and what's left is the noise. This is all the frequency bins without any filtering, and if you calculate the mean power, it will be minus 139.7. This is just a relative figure. I did not calibrate this in this graph. And if you remove all the radio signals, it will look like this, minus 152.9. So you really need to remove those strong radio transmissions to make a meaningful measurement. So I really would like to have more measurements because most measurements, as you saw, were from a very few people, a very few administrations in the world. And we could use more measurements to get a better picture of what the radio noise is really like. Especially quite rural measurements. And if you have any of those contributions, or if you want to do measurements, you can ask my my advice, no problem. You can find my email at the end of the presentation. And you can contribute measurements to the ITU via your administration or via the IARU. If you look back on the recording, you will find several references in the text. I put them over here. And my own publications are in between those publications you can download from ResearchGate. Okay, that was it for now. A little bit longer than I intended, but I'm ready to take questions.
Thank you very much, Ben. Are there any questions?
Yeah, I have one. You mentioned that vertical monopole with 6 radials on the ground. Would you comment on the effect of raising the radials off the ground that has to do with ground losses? So like elevated radials, say up maybe a tenth or 2/10 of a wavelength?
Yeah, good question. There are 2 aspects of raising the radials. One, it makes them a narrow band. So if you put them on the ground is absorbing a lot. So they're not actually resonant anymore. They only reduce the ground losses. If you elevate them, you have to make them quarter wave long, and you have to align the antenna. If you elevate them, the losses will be much lower. In this case, I didn't do that because I measured, I had to quickly produce results for the ITU. So I measured a couple of quite rural locations in the Netherlands on as many frequencies as I could. So I made a vertical antenna with switches in it, with connectors in it for 5 or 6 frequencies, and put that up. So I needed the ground system to be non-resonant. But of course, if it's higher up, it will be better. The efficiency we'll see will be higher, but that's not really the important point. The important point is that you will have to be able to model your antenna correctly, because you have to model your antenna to know what the ground losses are, because you have to compensate for it.
So you use modeling software to correct for the ground losses. I can see the ohmic losses you can measure, the mismatch loss you can calculate, the cable loss you can measure, but the ground loss is a little bit more complicated to me to figure out.
Yeah, so either you find out what the ground loss is by doing simulations with NEC4, for example, as accurate as you can, and with trying a lot of small variations in the lengths and heights, etc., to see if your values are correct. But of course, you need a lot of experience with the antenna modeling to know whether or not you can trust the models. If you don't, you need to calibrate the antenna by comparing it to a calibrated reference antenna and applying a known field.
Oh, okay. Thank you very much. Very, very nice presentation.
Yeah,
I have a question.
Yeah, go ahead.
the personal space weather station that's being constructed, it would seem like a good idea to create a noise measurement package or profile or some kind of standardized arrangement to use that with a specific setup and well-characterized antenna, although the ground, as you say, the ground characteristics would have a big effect. But if we could provide a standardized package that these could be installed, I doubt that they would be full calibrated quality, but you would have a lot of data. And sometimes that's very helpful as well. So we might want to consider that, Nathaniel. And then the other thing is Rudy Severns, November 6th, Lima Foxtrot, has done a lot of characterization of elevated and ground radials. And so he might have some good input on this question. Back to Nat.
Yes, okay. Yeah.
Yeah, I
Can I
think
react
this
on
is
that?
a really interesting topic. And I think you brought up something I didn't really appreciate before, Ben. This idea that a passive antenna can actually be more desirable, because a lot of my thinking so far has been an active antenna would be the way to go for this system. And I know a number of people have proposed different active antenna designs, but it seems with the different applications that we have for the personal space weather station, it seems like there's a number of competing kind of design goals here. So trying to reconcile all that might be a challenge, especially on the antenna end.
Yeah, that's correct.
Do you have any thoughts in terms of what would be a good general purpose antenna recommendation?
It depends very much on what you're going to do, Nathaniel. So first of all, to Ward, I know the work of NSYS 6LF already a long time. He also helped me for my DX station to put the best antenna lengths, radial lengths in the ground with a certain amount of money. On the personal space weather station for radio noise, it is not true that more data is better than less data that is calibrated. It is completely useless for the ITU to have a lot of measurements that we cannot relate to any absolute level of radio noise, an absolute level of field strength. So you need to have a calibrated system, you need to have a calibrated antenna. And there I agree with Nathaniel that there are a lot of different aspects of the personal space weather station. One of the things will be that people want to have a compact antenna, want to have a wideband antenna that generally please for an active antenna and not for a big passive monoband antenna or multiband antenna. Which still will make it possible to it's still possible to use it for the higher levels of radio noise if you can calibrate it, but it won't measure quiet rural.
Well, I think one thing that might be encouraging about this particular situation is that if quiet rural is where you really need the good noise measurements, maybe certain people who are in quiet rural locations optimize their system for that particular application, but maybe it's not a recommended application for people in general.
Yeah, I agree.
I've got a question. Now that we're talking possible receive antennas, I'm wondering, as you say, over much of the band, the noise is much greater than the receiver noise, so a little bit of loss in the antenna is not a problem. I'm wondering if a terminated folded dipole type or the vertical version would be a useful antenna. I know they're pretty lossy, but they're broadband.
Yeah, I started those measurements for the ITU. That was actually, the ITU meeting was in June, and I started in March, just scraping all my equipment together. And I started with designing a T2 FD or half T2 FD as a vertical over a ground plane. And it's nice. You can make it wideband enough, and of course it has a low gain. It's minus 20 to dBi at 3 megahertz and minus 6 dBi or so at 12 megahertz. So I thought, well, that will do the job because the interference is high enough at low frequencies and it falls off at higher frequencies. Even with my HPSDR, I cannot hear quiet rural radio noise with that one. So that is for quiet rural, that's about 6 to 10 dBs too insensitive. But maybe there's other solutions.
Interesting.
Other question.
I did.
Go ahead.
Ward.
Okay.
Ward and then Bill.
Ben, are you aware of the ARRL's noise characterization project? Ed Hare, W1 RFI, and Ned Stearns, AA7V, and Krista McIntyre, K6WB, I think, are all involved with that. There's some others as well, and they're trying to characterize background noise.
Yeah, I heard of that from Scotty when I gave last HamSCI presentation on NVIS. Okay. So I emailed with them. I don't have a two-way conversation yet. So they replied, they acknowledged, but there's no email text yet. So I don't know where they are. I need more information and I would like to exchange ideas with them because if they do, I would very much have information that I could also use in the ITU. So that means it's nice to characterize noise in a way that as a radio amateur, you think, I'm happy with this. But if the standard is quite different, you use is quite different from what is used in the ITU, it will not be acceptable there. So it would be much better if we could work together to get that done together.
Okay.
Bill, thank you, Bill, and then Dave.
Yeah, I've got another conference starting in just a few minutes, so I can't stay on here very long to discuss this, but I've been encouraged. Okay, I'm working on the Tangerine, and I've been encouraged to look at this whisper demon that has been proposed, put together by Rob Robinette and some other colleagues. They measure the noise that is on the band in between transmission time. So you have a few seconds between each 2-minute transmission on whisper. And it's just worth asking whether we could fold that in for some noise measurements, because we would have a lot of possible different folks that could run that. I mean, it's not trivial to use that with the Tangerine because it expects to be connected either to a Kiwi or to a sound card, apparently, from what I can determine so far. But all the code is freely available, apparently. So we may be able to. Yeah.
The idea would be interesting, especially because now we only have SNR from the whisper signals. There are two side effects on it. One is, of course, that to calibrate the measurements, again, you need a calibrated antenna. Secondly, you will be listening into a small segment of the spectrum that is quite intensely used. So if one person transmits out of sync, you will already have a higher level. Right. But we could test that by doing a measurement with a wider band receiver, like my streaming receiver, to get more of the spectrum and to see whether or not, for example, 7 megahertz whisper noise measurements concur with what we do with a different system.
Yeah. Because
you need to have some confidence before you input data into the ITU. It needs to be true.
Oh, absolutely. It would be necessary to compare it to well-calibrated reference and see if there's just too much random garbage thrown into it, or if it could actually be used for comparison. So back to Ned.
Question on that? Would it be better? So the Whisper Demon's only looking at this very narrow segment. The Tangerine is designed to be a broadband SDR. Would it be better to develop an independent mode that looked at the entire band and derive the noise measurement that way instead of getting it from Whisper Demon?
Oh, probably, yeah. I mean, you could certainly do that. The only reason I mentioned it was because a lot of people have suggested for me to look at Whisper Demon, and I'm trying to figure out what is the reason why I want to do that, because it's not not necessarily a trivial thing to make the Tangerine SDR interface with Whisper Demon. Not impossible, but there's a lot of work involved. We should only do it if we're going to get something good out of it.
Yeah,
It is not necessary if you want to measure noise.
Yeah,
If you look at this this picture, this is just what is it? 12 kilohertz of the receiver, stream to disk. And what I do to filter out the radio signals is for every FFT, I look at I sort the data that's in there. I have a nice way of making a threshold that cuts out all the radio signals, and everything else is left.
Yeah,
and from what is left, you just calculate the power.
Maybe we should talk about this a little bit more, Bill. But maybe if there is a better way to calculate the radio noise, you're right. Maybe we shouldn't spend the time trying to implement Whisper Demon, but instead try to implement that other way of calculating the noise.
Yeah, what you're showing here, Ben, is quite doable in the using the software I already have in Tangerine. It would just be a minor thing to add this technology into it. So
excellent, very
sorry,
interesting.
I have to go. I have another telco starting up with my team. So
thank you, Bill.
73, very good presentation, Ben. Thank you.
Thanks, Bill.
Dave Witten, go ahead.
Just a quick question. Is there a formal definition of, or I don't know how to say it. Is there a formal distinction between a quiet rural and a rural site that's not defined by the, if I have a site that I believe would be a quiet rural site, and I wished to go to the trouble of measuring it, would I think it, I think it's a likely site worth measuring. Is there a way to distinguish between what should be considered rural and quiet rural?
Yes, there is, of course. The ITU is very, very formal and procedure-like. Fortunately. So I often have discussions that we finally end up saying, okay, this is Witvliet against against 200 years of the ITU or something. But they did not have this good definitions of city, residential, rural, quiet rural in the past. So in the 60s. So when they redid the definitions, they have different names now. It's quiet rural is now called remote rural. Okay. And the definition is that the nearest house is, or nearest settlement, nearest house is 5 kilometers away. Okay. And there's also definitions for the other one. So they have clear definitions, which you can find in P372. And P372, you can just Google on internet, and it's open to the public. From the ITU, you can download the PDF.
Yes, I wondered that too. Okay.
And there's another recommendation about how to measure radio noise, and that is SM 1752 1753. So Sierra Mexico 1753. And that tells in a very complicated way on how to measure the measure radio noise, and it has all those new definitions of the environments already in. The P372 doesn't have it yet.
Very good.
And on your question with which you started, you have a very quiet area. Would you call it quiet rural? Me, as a radio person, would call it quiet rural. But in the Netherlands, it's very hard to find any location that's less than 5 kilometers away from any house or any power line or whatever. Because we're with 17 million people and in an area of 100 by 150 kilometers. Still, I found quiet rural locations radio-wise. And there's 1 or 2 locations that I could really go to on one of the islands that would be absolutely remote rural.
We have some very remote rural places in Antarctica that I have connections with. Would it be worthwhile trying to put a radio receiver down there to make those noise measurements?
Yeah, absolutely.
Yeah, we used to have them down there at the Agos. They've been pulled out.
Why did they get pulled out, Dave?
Because
Well, lack of funding and the fact that we're digitally interfaced rather than analog.
Do you think it would be feasible to get these types of measurements out of the AGOs again?
Yeah, of course. And in fact, we've got that data, just not recent.
Yeah, because Jim manages some HF experiments down there, right?
Well, we did. That's what I'm saying.
Yeah, yeah.
Until recently, we had our HF receivers running. You know, basically, well, 100 kilohertz to upwards of 5 megahertz.
So I guess
I also know that Alex Chartier did. Alex Chartier also did experiments. Yeah.
Mm-hmm.
But I know for an antenna he used the Wellbrook loop, so it will measure radio noise if it's loud.
Yeah, we have generally used the 3 meters on a side magnetic loop with a broadband preamp.
Okay. Mm-hmm.
And yeah, we'd be happy to get the receivers back there, but it's a matter of funding.
So I guess I have 2 questions for you, Ben. Number 1, what efforts do your team have to expand the locations of those remote rural locations? And 2, how long do you have to make a measurement at one of those locations for it to be considered a measurement?
Okay, the first question I didn't understand. Can you repeat that one?
Is the ITU study group actively expanding or trying to expand the number of quiet rural or remote rural locations?
Yeah, then you don't understand the structure of the ITU correctly. The ITU is nothing else than a meeting of experts of different countries, and is not an organization as such that has money to do experiments or similar things. It's just a group that collects data from other people, from administrations that did those measurements themselves, or from groups like the IARU that did measurements, scrutinize them, and if it's valid data, it will go to the database and it will be used.
So that means that in order to get more measurements, you'd have to get, like if we did have an experiment at the AGOs in Antarctica to measure this sort of thing, that would be something that would be very valuable.
Yes.
Okay. And similarly, if the Personal Space Weather Station, were set up, that would be something that would be very valuable.
Yes, absolutely.
Yeah. Now, I will mention that we are currently taking data at remote sites, both northern and southern hemisphere. At South Pole, we've got instruments still, and a number of places in the northern hemisphere.
And that'd be interesting. So then the question is that calibratable to produce radio noise figures?
Yeah, I don't know why not. It's a very standard receiving system that we use.
Okay, sounds very interesting. I'll be in touch.
That brings me back to I think a question we touched on before is about receive antennas, because I know in the Personal Space Weather Station we were looking for an example receive antenna that would be relatively easy to construct, relatively inexpensive, and sensitive enough to make proper measurements. Something that we could produce plans for, that we'd say, build your antenna like this, and therefore it will be able to be used to gather good data. Like you mentioned, one of your antennas wasn't sensitive enough to measure the data at certain frequencies. So we want to make sure that it would be sensitive enough to measure the data. So what comment could you make on what kind of antenna could we put together? I mean, even if we end up making it a kit that the hams could buy, that's inexpensive and relatively easy to construct, that it would become sort of like the standard antenna. Maybe not one you want to use all the time, but at least one that you could put up and you wouldn't have to measure a whole bunch of like coupling to ground and things that would be hard for the average ham to measure. Something that would be easy for him to get a good calibrated reading.
Yeah. Yeah, I know that is the big problem. Because what I wish, but when I was looking for quiet rural locations in the Netherlands, there are a couple of nature reserves that I cannot get into with a car. That would be ideal to do measurements. Then I have an ANN 200D. I've got a battery. I've got a big antenna. You've seen it. It's 10 meters long. How do I get that in the center of that nature reserve? That is my problem as well. So if you would have a Tangerine, that's already small and light. It probably draws less battery power than my HPSDR does. So I have a smaller battery. So next thing would be, how do I get a small and light antenna that I can put in my backpack, go into a nature reserve and do those measurements? That would be my ideal. I have looked at I have bought one of the DX engineering verticals, because those are meant to be for an array of low band DXing people. Still at low frequencies, I still hear the noise of the antenna above the ambient noise. So they're good at rural areas. Maybe they're good if you put them in an 8 array, but the single antennas are not good enough for quiet rural. That doesn't mean that it just is not good for a personal space weather station. For a personal space weather station, I would not use a vertical antenna, because you want to see ionosonts as well. So I would use a loop, for example. Loops are also less sensitive to ground. But then again, you would be happy if you could just buy them off the shelf, but they're all too noisy. And I had hoped that the LZ2AQ preamplifier was much better. I have one here. I've got 3 here. But I put it out.
The loops are noisy because they're active antennas, right?
Yeah, and the loops are quite small.
But you can't really build a passive loop very easily, right? I mean, there's not enough, it's not sensitive enough.
Passive loops are more sensitive, but because you make them a narrow band. So you tune them.
Okay.
But that's not what you want. Also not for radio noise measurements, because if the tuning is 1 kilohertz off, you have a different antenna factor.
Right. So
and I had a quick question. This is following up with Nathaniel's question, the second question he had, but say you were to put a receiver and an antenna in a backpack and go into the nature preserve, how long would you need to stay there and collect in order for it to be a valid measurement that would be useful to the ITU?
Yeah, sorry, I forgot to answer that. Half an hour to an hour is absolute minimum. Because what you normally would do is you would stick on in one location and measure as many frequencies in parallel as possible. So that's also interesting application for the Orange SDR. And then you can stay on one location longer, because you might measure 20 frequencies or so. And if you would measure them over 24 hours, you would see the propagation as well on all those frequencies. So the ITU radio noise database, of which I am the table keeper, has slots for 1 hour to put your data in. So it's one line for a location and a date and location, and then there's slots for every hour. But I've seen from my own measurements that if you measure on a clear frequency, measuring 6 minutes or 10 minutes already gives you the value that you would always have. So measuring half an hour to an hour would be sufficient to convince the ITU that it's a good measurement for that particular hour, that particular day, that particular location.
Do you account for solar cycle or seasonal variations as well?
Yes, we do, but the database is much too sparse. So what we have is much too sparse to really see all those changes and then put that in to a model. So the model, as you see from the graph that I've got on the screen now, is very primitive. And we would be happy if we had information over more years, because also then you would be able to say to the people that work in my same company or in CISPR or in ITU on EMC norms, you could say, sorry, but this is not going the right way. On 1 megahertz, the noise has been increasing by 10 dB in 10 years. So we would like to have all that information. So not only propagation related, but also man-made noise equipment density and equipment quality related.
So really what you need is a latitudinal, I guess a longitudinal chain from the northern hemisphere to the southern hemisphere of monitors located in quiet rural locations that are monitoring 24/7 for multiple solar cycles.
Yeah, that would be beautiful.
Okay.
And then not just north-south, but just randomly around the globe.
Randomly around. Okay, yeah.
Yeah.
So at all latitudes and longitudes.
Yes. And that could also be expeditions. So if I had the time and if I had a portable system that would not be confiscated at the airport, once I go to Kenya to deliver a lecture over there, I would take that stuff with me and do measurements over there. Because Kenya will never do those measurements. And similarly, also in Europe, it's only Germany, the Netherlands, the UK that did measurements. I need them from Portugal, I need them from Spain, I need them from Italy, I need them from Yugoslavia, I need them from Poland. So that really begs for just jumping in a car and doing measurements. And then any measurement is better than nothing because we don't have any.
I feel like the real linchpin in this whole system right now is the antenna situation, because it sounds like, you know, we have hardware and we have ways of either time sharing the hardware between different applications, or, you know, deriving various measurements from IQ streams or whatever. We can do all sorts of clever things and algorithms, but it sounds like trying to get a well calibrated antenna that's applicable for, you know, that anyone can set up rapidly and would work in many different situations sounds really challenging. So
Yeah, well, the antennas we use are definitely, the calibration can be calculated. We know that what it is, and they're sensitive enough to pick up auroral hiss and the aurora roars and all that. So yeah, they're pretty sensitive systems.
Yeah,
that'd be good, because
is it true that you also do measurements on VLF, Ward, or was that somebody else that I remembered?
VLF is the Stanford guys. We get
Okay,
down
good.
to about 100 kilohertz.
Yeah, because we don't have many measurements on low frequency, so I don't know what noise is like on low frequencies.
Right, but we have a lot of people on the HamSCI / Tangerine project that are ex-Stanford or traceable back. So, and in fact, we're working on a VLF board for that receiver.
Tangerine, yeah.
Okay, good.
yeah, my student's very interested in that. But yeah, like Ward, if we were able to say, you know, replace the RBN receivers, the RBN only receivers that Yasmin's putting out in these exotic locations, if we were able to get something that could not only give RBN but also these noise
Wow.
measurements
Yeah.
and
Yeah.
things like that, that would be a really, it sounds very valuable.
That would be great.
What constitutes a ground plane on a glacier? I'm just asking.
Actually, it's interesting you asked that, because the dielectric constant of the snow is significant and does change propagation.
Because
Right.
I have a brother-in-law who's an extreme mountain climber, kind of world class, and he's, you know, you talk about quiet sites. Some of the backsides of some of those places in southern China and northern India or Nepal are pretty out of the way.
Yeah.
And
Yeah.
then telescope sites, you know, just sighting for, you know, in Hawaii and you know, in Peru and wherever.
Yeah, sure. We just have to have get a receiver there. So what the easiest way would be if people already are at some places and have a receiver somewhere that they do measurements, and then you only have to add the antenna.
Well, I think we're about 15 minutes over our time slot right now. So I'll probably do is I'll probably close the formal session. But first of all, I would like to very much thank you, Ben, for giving us 2 excellent talks. one right after the other. And I think they've both been extremely helpful. I think this talk today, I think, has been particularly enlightening to me, and I think to many other people on the Personal Space Weather Station project, because I think it helps put into perspective, certainly from, radio amateurs certainly can very much appreciate the need for these sorts of measurements. And I think understanding the importance of these quiet rural measurements is very important. I did not understand that, if the ITU curves go up, that's actually bad for us.
Yes.
So I think understanding that we need to make those, find the quietest locations as possible and show that they still exist. I think that's a really nice kind of mandate that a lot of us can understand. So I think those, knowing that those areas are of interest to hams and to the ITU, I think that's very important. And I think those areas are also going to be of interest to people who are interested in naturally generated noise signatures from a science perspective as well. So
Yes.
I think that's a very valuable target, and I think that might help guide our decisions regarding things like antenna design and things like that. So I hope that we'll be able to have you back again in the near future, and that we can iterate with you maybe on antenna designs and some other design issues with the Tangerine, and maybe if you do have any brilliant ideas on good antenna recommendations, that we hope that you would let us know.
Yeah, sure. And also, reversely, if one of your students have a great idea of making adaptive filters for single carrier noise, I would also be happy.
Yeah, that would be good. And maybe you said you didn't have time to talk about each of these different particular types of noise today. Maybe in the future you'd want to go more in depth on one and present some additional problems that people might be able to work on, because I think it's always good to know not only what we do know already, but where are the open questions and what are the problems that need to be solved, because I think that's what a lot of people here are actually interested in.
Good. Okay.
All right. So thank you very much. Let's give Ben one last round of applause, if not virtually. And
Thank you, Ben. It was a fantastic presentation. Got a lot out of it.
Thanks, John. Thank you all for listening, for putting up with me, and it was a joy to present here.
Well, the joy is ours.
A couple other advertisements. Let's see. I don't have it confirmed yet, but I'm hoping we don't officially have a speaker for the next HamSCI workshop or HamSCI Telecon. The next HamSCI Telecon, I think, would normally fall on Thanksgiving. We're not having a HamSCI Telecon on Thanksgiving. It's not going to happen. So everyone's saying yes. So it'll probably be. I'm not going to change the schedule. We'll just cancel that one. We have the American Geophysical Union meeting December 1st through 17th, which people are getting ready for. So I think the next HamSCI Telecon will be that middle Thursday in, let's see, I think it'll be December 10th. And so I'll email people about that. I'm going to try to get one of my students, Diego, to give a talk on his work that he's been doing. He's been continuing the TID RBN WhisperNet research. And he's putting together a presentation poster for the NEROC meeting this coming week, and also for AGU. So I hope that I can get him to give a presentation. I think I will. I'm still open for other people giving presentations. So if you have something you'd like to talk about, please email me and we'd be happy to have you talk. And one other advertisement, the Radio Club of America, they're having their seminar November 21st, and it's going to be virtual. So that's not this Saturday, but next Saturday. And I'm giving the first talk of the day for that one, which will be on traveling atmospheric disturbances in the Ambient and Whisper. I'm also giving the last talk of the day. I'm doing the keynote talk, which I'm still have to write. So if anyone has some things they want me to talk about in the keynote, send me an email and maybe I'll include that too. So
Nathaniel, could you
yes.
send out an announcement about that so we can make it a point to tune in?
Sure, I can forward some information about that. Yes, and
Thank you.
I think, and we have one. I have a special guest who's gonna say hi before we sign off here. And here's Rachel. And come on, turn off. Can't get my. Why did my background? Come here, Anthony. There. Look at that.
Wow.
Yeah. So
There he is.
Anthony is going to say hi as well. So. Okay. So thank
So
you
when's
very
he
much.
getting his license?
Oh, I don't know. He sure has been trying to play with my radio every time he comes in here. He loves spinning the knobs and things like that.
Did you get
I
him his
believe
own
the
radio?
youngest ham on record was age 4.
4. Wow.
Yeah,
I
got
don't-
his novice license, and I think that was in the 60s or 70s, but don't hold me to that.
Oh
It
man,
was announced at Hamvention.
that's a tall order. I'm
Just
still
give him
trying
a-
to.
Give him one of those things called a Morse code key, I think they're called.
Yeah, we have one right over here that he's been playing with. I've still been trying to get him to say magnetohydrodynamics, but he's not quite there yet. So I don't know.
That'll be done by the end of the week, I'm sure.
Yes, definitely. Great. Say hi, Anthony. Good, everyone. Thank you very much. Okay.
Everybody stay
7:30.
healthy.
7-3.
Thank
Happy
you.
Gobble Day, everybody.
Thank you.
7-3
Yes,
all.
happy Thanksgiving. 7-3.